Okay, guys. Okay, so good morning, everyone. Today I'm going to give the second part of my seminar. So I want to begin by presenting some ideas about Euclidean field theories, particularly 5-4 theories. I really like this reference, critical properties of 5-4 theories. These are the authors. Now I want to present some ideas about these theories. Okay, let me begin with this idea. Okay, any fluctuating field is an object of this form, where each entry is a function from Rd into R. Okay, the field components interact with each other via a term of 4 order in the field. This is the interaction term. Okay, so lambda is the coupling constant, and T sub alpha, beta, gamma, delta is the coupling tensor, and phi alpha, phi beta, phi gamma, and phi delta are the fields. Okay. Now, this is the fundamental physical hypothesis. The field phi performs thermal fluctuations. Okay. In the investigation of these objects, in the construction of these theories, typically one assumes that the expectation value of the field is 0. This means that the field or fields perform fluctuations around the 0, around the origin. Okay? Assuming this hypothesis, the size of the fluctuation is controlled by an energy functional. This is the energy functional. 2.1 defines the energy functional of the theory. This functional has 2 parts, E0, and the E0 is the so-called free energy, and E sub interaction is the interaction energy. The first term, which is the free field energy, is a kinetic term. Okay, basically this is kinetic energy. Okay, this is, let's say, this is the speed, the square of the speed. Okay, so this is a kinetic energy. The second term is the interaction term. In this case, we are using a 5-4 term. For this reason, we say that we are working with a 5-4 theory. Okay, and lambda is the coupling constant of the theory. The parameter m, this parameter m, is the mass of the theory. By the way, that you can interrupt at any time. Now, the thermodynamic properties of the system are controlled by the partition function. This is the partition function. Okay, so basically here we have exponential minus the energy divided by this constant. This is the Boltzmann factor. Okay, if the energy is very high, then the probability of occupying this high energy configuration is very small. On the other side, if the energy at phi is very small, then the probability of occupying this state is high. This d phi is a measure, is a pseudo measure. Okay, here kd is the Boltzmann constant and T is the temperature. The measure of the functional integration is defined by the product of the integrals at each space at the point x multiplied by some irrelevant normalization constant. Okay, this is the definition of the measure given by the physicist, but this measure is ill-defined. Okay, so 2.4 defines the partition function of the theory. Now, typically, one takes this normalization. The product of the Boltzmann constant times temperature is 1. So the partition function takes this form. Okay. Now, This partition, if we take lambda 0, remember that this energy functional depends on lambda. If lambda is 0, this means that the energy functional doesn't contain the interaction term. This Z0 is this functional, is the value of this functional when lambda is 0, okay? Now, we can say, from a mathematical perspective, an Euclidean, this is very important, Euclidean, an Euclidean quantum field theory is an ill-defined probability measure of this form. This is the probability measure, okay? This is the Boltzmann factor, this is the normalization constant, and this is the measure. This is a fictional measure. And this measure is supposed to be a probability measure on the space of fields, okay? Now, the partition function 2.4 describes all the thermodynamic properties of the system. It doesn't give any information on the local properties of the system which are observed in scattering experiments, okay? This information is carried by the correlation functions of the field, okay? So here you have the definition 2.10 gives the definition of the endpoint correlation function. There are endpoints. Notice that the mean of this is a number, this is the average of the measures, this is the expected value of the values of the fields at the points x1 up to xn. This is an expected value with respect to this measure, okay? So we multiply the function by the measure, and then we integrate over all the possible fields. So this is just a momenta of a probability measure, okay? These functions are also called endpoint green functions. Now, the next step of the next goal is to describe or to compute these functions. There is a compact way of describing all the correlation functions of the system with help of one functional object. One introduces an auxiliary field, J, called a current, and adds to the energy functional a linear interaction energy of this current with the field. So now we define a new energy functional we call source. And this is the definition of this energy functional. We multiply, it is basically the inner product of the field with respect to the current. Here we are assuming that n is 1. We are working just with one field, okay? Now, oops, sorry. So now the total energy is E plus the neutron. Now there is a partition function corresponding to this energy, to the functional 2.12. This partition function is denoted in this way, Cj, because it depends on J, and this is the definition of this partition function, okay? Now, this is a generating function for the endpoint correlation functions. Why? Because the endpoint correlation functions can be computed by using this rule, by using this formula. We compute derivatives with respect to the parameters. These are functional derivatives. I don't have time to explain this, but by computing these derivatives and replacing J by 0, we obtain the correlation, this correlation function, okay? So the goal, the central goal, is to compute, in quantum field theory, is to compute these functions. This calculation is quite complicated. In the calculation of these functions appears the Feynman diagrams. Okay, do you have comments or questions? This is just a very short introduction to the 5-4 theories. Now, I want to present some ideas about quantum field theories and neural networks in the p-adic framework. So this is an ongoing project. So let me begin by recalling the definition of the p-adic numbers. So the field of p-adic numbers, denoted as QP, is defined as the completion of the field of rational numbers with respect to the p-adic norm. Okay, the p-adic norm of a rational number is defined in this way. Of course, if x is 0, the p-adic norm must be 0. If x is different from 0, then x is a rational number. X can be represented as a power of p times a fraction, where a and b are co-prime with p. So the number gamma is uniquely defined by x and p. This gamma, this integer gamma, is the p-adic order of x. Okay, by definition, the order of 0 is plus infinity. Now, QP, of course, this norm indulges a distance, and then QP is a metric space. Indeed, QP is a complete ultrametric space. Ultrametric means that the norm satisfies this inequality. This inequality is stronger than the classical triangle inequality. QP is a fractal, more precisely, as a topological space. QP is homeomorphic to a Cantor-like subset of the real line of R. Now, any p-adic number different from 0 can be represented in this form. It's a series of this form. In this series, the xj are p-adic digits. In other words, Sj is an element of this set. We have to take, it is necessary to take x0 different of 0. Okay. Then this power of p is well defined due to this condition. Okay. Then any p-adic number different from 0 it can be represented as a power of p to the order of x times another p-adic number. And the norm of this, the p-adic norm of x is exactly p to the minus the order of x. As I said, QP is a metric space. So this symbol denotes the ball with center at A and radius p to the r. Okay, so this is the set of all points in QP such that the distance to the center is less than or equal to p to the r. Okay. Okay, we use this notation if the center is 0. If r is 0, V0 is the unit ball, and in this case, the unit ball is a ring, is the ring of p-adic integers. We use this symbol to denote the sphere with center in A and radius p to the r. Okay, if the center is 0, we use this notation. Okay. The balls and spheres are both open and closed subsets in QP. In addition, two balls in QP are either disjoint or one is contained in the other. As a topological space, QP is totally disconnected. This means that the only connected subsets of QP are the empty set and the points. Here there is a typo. It should be n should be 1. Okay. A subset of QP is compact if and only if it is closed and bounded. Okay. Then the balls and the spheres are compact subsets. As a consequence of this, QP, this metric space is a locally compact topological space because the balls are compact subsets. Now, QP with the sum is a group and also a topological space. Since the sum is a continuous function with respect to the topology, QP, this group is a locally compact topological group. There is a theorem called the Haar theorem. This theorem asserts that there exists a Haar measure, dx, which is invariant under translation. This is a symbolic representation of this assertion of the invariance under translation. If we normalize the measure by this condition, in other words, if we assume that the measure of the unit ball is 1, then the higher measure is uniquely defined. Okay, I'm going to use this notation, this capital omega, to denote the characteristic function of the ball of radius r or p to the r at center A. For more general sets, I'm going to use this notation for the characteristic function. Okay. Now, the Bruhat-Schwarz space. Okay. We work here with complex valued functions defined on QP. A function phi is called locally constant if given any point in the domain, there is an integer depending on x such that identity 1 holds. What is the meaning of 1? The value of the function at x doesn't change if we perturb x by x prime, where x prime is very small. If x prime belongs to a small ball around the origin, the value of the function doesn't change. Okay, the function is locally constant. Now, a function of this form is called a test function or a Bruhat-Schwarz function if it is locally constant. It is locally constant with compact support. Any test function can be represented as a linear combination with complex coefficients of characteristic functions of balls. Okay, I'm going to use this letter, this calligraphic D, to denote the C vector space of test function. And I'm going to use this notation to denote the R vector space of test functions. Okay. Now, if phi is a test function, in other words, if phi has compact support, then this number L can be chosen independent on the X. And in this case, the largest possible value of L is called the parameter of local constancy of the function phi. Okay. Now, if U is an open set of QP, this symbol du denotes the C vector space of all test functions supported with support contained in U. Now I'm going to introduce the p-adic analogs of the phi for quantum field theories. I'm going to fix 4 functions, A, B, C, D. These are test functions, real value test functions supported in the unit ball. Okay, so all these functions are defined in the unit ball. Also, I need a radial function. Okay, notice that this is a composition of a real function with the p-adic node. Okay, now an Euclidean field. Now I'm working with 2 fields, phi and psi, is a generalized stochastic process in this space. Okay, this is a technical definition. Now, here is the physical interpretation. The field performs thermal fluctuation, assuming that the expectation value of the field is 0, the fluctuations take place around 0. Here I am following the reference that I mentioned before. The size of the fluctuation is controlled by the following energy functional or action. So here, E is the energy functional. W, A, B, C, and D are parameters. The energy functional has 2 parts or 2 components. A0 is the free field part, and this is the interaction energy. Okay, this is the first term. Notice that now this is the kinetic term. Here we have, this first operator or functional plays the role of, I mean, this is the kinetic term, okay? Now, in this case, I am using two linear terms, okay? And these are the mass terms, okay? Notice that the mass is fixed. Okay, now this is the interaction term. The interaction term is a 5-4 term. Now we have two 5-4 terms, one for the first field and one for the second field. Now the coupling constants are functions, okay? Now, again, all the thermodynamic properties of the system are described by the partition function of the fluctuating field. This is the definition of the partition function, okay? This is the Boltzmann factor. Notice that here I'm using, let me increase the size. Here, the energy functional depends on two fields, okay, phi and psi. Again, we use this normalization, okay, and this measure is an ill-defined, okay. It is expected that such measure can be defined rigorously by a limit process. Okay. Now, the information about the local properties of the system is contained in the correlation functions of endpoints, okay? Now, in order to define the correlation functions of endpoints, I need two sets, I and K. I and K are subsets of this set, and I and K are disjoint subsets, okay? So this is the end correlation function. I have to take the correlation function is the expected value of this function. Is the expected value of this function with respect to this measure, okay? Now, these functions are also called the endpoint green functions. To study these functions, one introduces two auxiliary external fields. Now I need two external fields. Why? Because I have two fields, phi and psi. Here there is a typo. This is the unit ball, okay? So this is the energy associated with these two currents, okay? So this is the inner product, the L2 inner product of J0 with respect to the first field, the inner product of J1 with respect to the second field. Now we have a new energy functional. This is the new energy functional. And this is the partition function. Now the partition function depends on the currents J0 and J1. Okay. Now, the functional derivatives of this generated functional with respect to J0 and J1 evaluated at J0 equals 0, J1 equals 0, give the correlation function, the correlation functions of the system. More precisely, we can compute this correlation function using this recipe, okay? For this reason, this functional is called the generating functional of the theorem, okay? So here I presented a p-adic analog of the classical construction of a 5-4 theorem given used by the physicists, okay? So this is formal. Notice that this is completely formal. Now, discretization of the energy functional. Okay, GL is defined by GL is a finite group, and more precisely, GL is a quotient group. It is an additive quotient group. This is a system of representatives of the elements of GL. Okay, now I'm going to introduce this subspace. This is the R vector space of all test functions of this form. Okay. Now, this is a finite sum. I runs through this finite group. This is the value of the function at the point I, and this is the characteristic function of the ball with center at I and radius p to the minus L. Okay, so this capital omega is the characteristic function of this ball. Okay, and the function phi is supported, this function is supported in the unit ball. Okay, it is important that these functions, the omegas, are linearly independent. Okay, so this is a finite dimension. This vector space has finite dimension, and the dimension of this space is the number, is the cardinality of this group. Okay, from now on, I'm going to identify a function in this space with this vector. It is important that this function, this is subspace, this space, or this DL is a subspace of the space of test functions. This is a very particular fact. There is no an analog version of this result in the Archimedean case. Okay, I mean, in the Archimedean case, the discretization of a Schwarz function is not a Schwarz function. Here, in the periodic case, the discretization of a Bruhat-Schwarz function belongs to the Bruhat-Schwarz space. Okay, basically, I mean, this means that really all the test functions or Bruhat-Schwarz functions are discrete objects. Okay, here we have some mathematical observations. For instance, that the space of test function supported in the unit ball is the direct limit of this space. Okay, now E is a functional defined on this space. DL is a subspace. Then we can restrict this functional to DL, and we denote this restriction by this symbol. Okay. Now, the next step is to find an explicit formula for this functional. In order to do that, we have to assume that the fields phi and psi are elements in this vector space. This means that phi and psi have this representation. Now, if we multiply omega, which is a radial function, by the characteristic function of these balls, then we have that this function, this product is this number times this function if the points are different. Now, if I is equal to j, we have this expression. Okay. Now, we have to compute this product. Okay. The product of A times the characteristic function, sorry, of this ball. Okay. In order to do this, we have to remember that A is a test function, which means that A is locally constant. Then and this omega is the characteristic function of a ball. If the radius of this ball is very small, which this means if L is large, then the value of the function of this function restricted to the support of this function is constant. More precisely, is this number. Okay, so this argument is valid for the function b, c, and d. Now, if we replace if we have to represent all these functions in this base, and if we replace all the functions in this functional and do some calculations, we get this expression. Okay, so basically we get this expression. This is the discretization of the integral involving, this is the discretization of the integral involving the kernel W. Okay, this is the discretization of the linear term involving phi, the discretization of the linear term involving the second field, these are the mass terms. And here there is a typo. This should be 5.4. Okay, and these are these two terms correspond to the discretization of the interaction terms. Okay, now I'm going to change the notation. Instead of this phi of I, I'm going to use phi sub I. I'm going to change this notation. Okay. Then instead of p to the minus L, A of I, I'm going to use A sub I, and so on. By using this notation, we obtain this discretization. So this is the energy functional of a discrete version of a 5.4 theory. This is I mean, this functional is similar to the one that I presented in my first seminar. The difference is that in this functional, the indices run through GL, and GL is a finite ultrametric space. In my first seminar, the indices in the function that I presented in my first seminar, instead of GL, we have a square lattice. Okay. Comments or questions? Now, the next step. Yes, go ahead.
So why do you need pairs of fields in order to take it over to the non-Archimedean case? Will you tell?
No, the motivation, I mean, this 5.4 theory was constructed to match the theory introduced in the paper that I presented in my first seminar. That's the motivation. Okay, so the purpose of using, or we need two fields because we want to construct a p-adic analog of certain neural networks. For this reason, I need two fields. Okay.
So the point, I think, so you're saying that the point basically of the calculation is you're trying to calculate an expected value, and this is where you cross terms.
Now let me introduce. Okay, one important thing before continuing. It is important to remember that GL is an additive group. Then this sum can be represented in this way. Okay, by using this observation, the discrete energy functional can be rewritten in this way. Now I'm using omega. Omega denotes the parameters, the W, the A, the B, the C, and so on. Okay, so EL is the energy functional for a discrete 5.4 theory. In phi, this is the paper that I presented in my first seminar. A similar energy functional was considered in connection with machine learning. However, there are two crucial differences. First, here the elements of GL are the vertices at the top level of a rooted tree with L plus 1 levels, and with P to the L vertices at level L. While in phi, A squared lattice is used. Second, the action EL is non-local, which means that in general, these coupling constants are different from 0 for any ij in GL. While in phi, these coupling constants are different from 0 only in the case in which I and j are connected by one edge. This condition for any ij in GL means that all the neurons interact each other, but GL is not a fully connected graph. Okay, so this is the motivation for introducing this energy functional is to construct a p-adic analog of the neural networks introduced in this paper. Okay, I'm gonna construct this p-adic version right now. The next step is to introduce a Boltzmann-Gibbs probability distribution. Okay. From now on, I'm going to use this notation phi. I'm going to identify phi with this vector and psi with this vector. Okay. So for this reason, I'm going to use this notation. Now, this is the Boltzmann-Gibbs probability distribution attached to this energy functional. So it's exponential of minus the energy functional, and then we have to divide by z, and z is the partition function. Okay. So this is the Boltzmann-Gibbs probability. Now, this is important due to the fact that for a general value of the parameter theta, we have this condition for any ij in GL, the probability distribution doesn't satisfy the Hammersley-Clifford theorem, while the distribution considered in this paper satisfies. Now, it is expected that the limit of this probability distribution, notice that here I'm assuming that this is a function in, let me try to write, okay. So I'm assuming that this is a function, that PL is a function in this space. Here I have to put the cardinality of GL, and then I need a second copy, okay? For this reason, this is the Ledeck measure on this space, okay? So it is expected that if we take the limit of this discrete Boltzmann-Gibbs probability function, we get a quantum field theory, okay? Of course, this is a difficult mathematical problem. But the interesting thing is that for applications to machine learning, we do not need this object. We just need this object. But if we know this probability distribution, I mean this probability measure, then we can use, I mean the correlation functions attached to this measure give information about the neural network attached to PL. Okay, this approach appears in certain papers already published. Okay, now I'm going to introduce the p-adic analogs of the neural networks presented in the paper in the publication part. Okay, we now identify GL. Let me change with the set of branches, vertices at the top level of a rooted tree with L+1 levels and P to the L branches. We attach to each branch two random variables. Okay. The visible field is defined as, so this collection of random variables is the visible field, and this collection of random variables is the hidden field. Okay. The variables phi I, phi j, respectively, psi I, psi j, are independent under this hypothesis. This is important. Now,
so sorry, Wilson.
Yes.
So is this basically this is a kind of a generalization of the notion then of a hidden Markov process?
Yes, yes, but here, I mean, this is a very important point. I cannot use the a Markov field or on a graph. So this is in certain sense, this is a generalization. I have to read more about these objects, but it is important that this famous theorem of Hammersley-Clifford is not valid in this framework.
I see. Interesting.
So this is the idea. Basically, a p-adic neural network is characterized by this probability distribution. Okay, let me write. By constructing a suitable algorithm for updating the parameters theta, this network can learn a probability distribution. That's the idea. If we construct a learning algorithm, is an algorithm to update these parameters, and by this procedure, this network can learn a probability distribution. In other words, PL can approximate another probability distribution. And this is learning in this framework. Okay, now I computed some expressions that these expressions are required to do calculations. I think that these expressions are required to implement these neural networks. Okay, so we know the joint distribution. The joint distribution of the visible field and the hidden field is given by 6. So this is the joint distribution. This is the joint distribution of the visible field and the hidden field. Okay, now the marginal probability distribution is given in this way. To compute the marginal probability distribution with respect to phi, we have to integrate with respect to the other field. Okay, if we do the calculations, we get, I mean, this expression, we get this expression. Okay, and this is the marginal probability distribution for the hidden field. Okay, is given by this expression. Now it is important to study the conditional probability distribution. The variables, these variables are connected through this way. Okay, by fixing the hidden field, these variables become independent. Okay, an analog assertion is valid if we fix the visible field. This is an intuitive assertion, guys. Anyway, I think it is important to check that this intuition is true. In other words, we have to verify these two formulas. Okay, this is the conditional probability of the visible field given the hidden field. And here we have that this probability distribution is a product of this conditional distribution. Okay, this is a similar assertion for the hidden field. So I did this calculation. This is a boring calculation. It's a very long, boring calculation. This is elementary. Of course, it is necessary to do the calculations carefully. Now, in order, remember that in order to implement an algorithm, let me try to write here. Okay, we need, or we have to update the parameters of the network. Okay, so these are the parameters of the network at the time t+1. These parameters, the new parameters, are computed from the parameters at the time t. And here there is a constant, the learning constant, and here we need a gradient. Okay, here we need the gradient of the log likelihood function, which is this function. Okay, now for practical purposes, okay, I mean, we need to compute this expression. Okay, this is just calculus. Okay, so okay, let us compute. Let me give you some details. This is very simple. So we have to compute the derivative, the partial derivative with respect to theta. Remember that theta is a list of parameters, so this is just a symbolic notation. Now we have to compute, or we can compute this probability by using this expression. This means that we start with the joint probability between these two fields, and we compute this probability PL phi as a marginal probability. Now we take the logarithm of the numerator minus the logarithm of the denominator, and we do the calculation. Okay, I'm going to skip this. So at the end, we get an expression of this form. We get that this derivative minus this derivative is the average of this function with respect to this distribution minus, here we have first the average with respect to the distribution, and then we have to compute the average with respect to the distribution. Now, the implementation or the computation of the practical computation of this expression is quite complicated. It's non-trivial. So there is an algorithm called the contrasted divergence. By using this algorithm, it's possible to implement this calculation in a practical way. I'm going to skip this. Now, that really, we don't, in the implementation, we have to use a different log likelihood function. Okay, this is the situation. In the practice, unusual, this is a deep belief network is fed with a data set. Okay, then its parameters, these are the parameters, are tuned such that the equilibrium properties of the learned network reproduce faithfully the correlation or patterns present in the data set. Okay, in the periodic case, there is no rule for finding the tree. In other words, for selecting P and L, then it is necessary to test several trees, which means that for a given L, GL is necessary to compute the parameters and then select the tree or the network that best explain the given data set. Now, suppose that we have a set of data points. So this means that we have realizations of this field phi sub I. These are realizations of this field. Indeed, we have n samples, okay, of this field. Now, with these n samples, we have to construct a log likelihood function. Notice this is so. Here, this is the probability of phi of the visible field, but now notice that we use the data. Notice that this is the joint probability between the visible and the hidden field, but now here we are using the data that we have. Okay, we have to sum of the hidden field to obtain the marginal probability distribution for the visible field. Okay, so now we have to work with this expression, and we have to repeat the calculations that we did before. But notice that here there is something new. We have an average involving the data set. Okay, now it is necessary to do all these calculations because we need the gradient. Okay. Here we have the answer. Let me see the answer. Okay, what is the answer? Okay. This is the derivative of the log likelihood of the log likelihood function with respect to the parameter AK, BK, CK, DK, and this is, I think that this large expression is the derivative of the log likelihood function with respect to the WK. Okay, let me go back to the beginning. Yes. Okay. This derivative is given by this expression. Okay, now the next step is to implement the network and then try to test the network using real data. Right now, we are trying to do the implementation, and the next step is to test the network to see if the network can do something useful. Okay. So this is the end of my seminar, guys. Thank you for your attention. Do you have comments or questions? Let me stop sharing. Stop recording.